we talked about permutation. If we have a collection of values or objects, in how many ways we can select some of them and write them in order. Now the question is, what if ordering is not important? So, question. What if ordering is not important? Do we get the exact same number of ways of like arranging objects? Again, arranging objects, ordering objects, we know that they are equivalent to each other. So how many ways we can select those and just form a collection or subset of those objects or numbers? In this case, we are actually dealing with combinations. So permutations, ordering, and combination. Over one example to actually feel more comfortable about combination versus permutation. Okay, in this example, we have 4 letters, A, B, C, D, and our goal is to just select 3 letters out of those 4 letters, first using ordering, second without caring about ordering. How many ways we can select 3 letters out of A, B, C, D with ordering, without ordering. So ordering is not important for us. We're just going to select 3 out of 4. But in this case, we care about the arrangement in a row or order. So suppose your first letter that you selected is A. For A, you have 3 options. It can be B, next value, next number, take the second place, or it can be C, or it can be D. For letter B, you have either C or D. Well, for C, you have 2 options. It can be B, then D, and then if you're selecting D, you have the option of having B or C. So it means that you have A, B, C, then you have A, B, D, then A, C, B, then A, C, D, of course A, D, B, and A, D, C. Very well. So we have the same tree for B. For B, as the very first letter, you have the option to have C, or you have A, or you have D. Very well. For C, then we have A, then we have D, the third place. After A, you can choose C, or you can choose D. After D, you can choose C, or you can choose A. So how many? B, C, A, B, C, D, B, A, C, B, A, D, then B, D, C, then B, D, A. Okay, and we can continue this process. Very well. Next one, C. For C, we have these options: C, A, B, and D. A, then you can select B or D. After B, you can select A or D. After D, you can select A or B. So you have CAB, CAB, then you have CAD. Ordering is important for us. CBA, then CBD, then CDA, then CDB. And finally, if your very first letter is D, you're going to have the same process. For D, we have A, or B, or C. After A, you can select B, or you can select C. After B, you can select A, or you can select C. And after C, you can select A, or you can select B. So DAB, DAB, DAC. Then DBA, DBA, DBC, DCA, DCA, DCB, DC, and B. Well, how many permutations? 1, 2, 3, 4, 5, 6, and 4, 26 times 4, or 4 times 6, 24 different permutations or ordering is available. Without ordering, how many options do we have? So it can be A, B, C, or it can be A, B, D. Ordering is not important, we're just selecting 3 letters. It can be B, C, D. What else do we have? A, C, D. Do we have any other combination of 3 letters out of 4 letters? Just 4. 1, 2, 3, 4. Very well. So we have 4 different selections. So as you can see, we have 24 permutations or selection with ordering. But if you just want to select 3 of them out of 4 of them, it's going to be 4 different selections or 4 different choices. This method is called combination, and this method is called permutation. Very well. So take a look at this. For each combination, DAB, DAC, DBA, DBC, DCA, DCB, and the rest of them. How many different orderings do we have? So I'm just going to focus on one of these. Let's say DAB. I have DAB, then I have, I'm looking for BDA, okay, then, okay, BDA. These are exactly the same. ABD, ABD. The ordering is different from each other. Then I'm looking for ABB, ADB, or ABD, ABD, ADB. And also, if I'm looking at this, I'm looking for DBA as well. So DBA, very well. And here we have BAD, I'm looking for BAD, excellent. So 1, 2, 3, 4, 5, 6. 6 for each of these 3 letters, like DAB, we're going to have 6 different orderings. 6 different orderings. So take a look at this. I'm going to draw a formula using the permutation. So in permutation, you learn that, okay, the permutation of R objects out of N objects is N factorial divided by N minus R factorial. So in this case, I'm selecting 3 objects out of 4 objects. So on the numerator, I have 4 factorial. On the denominator, what do I have? I have 4 minus 3 factorial. So this is just 1 factorial. So the permutation of 4 and 3 is equal to 4 factorial divided by 1 factorial, which is 4 factorial. 4 times 3 times 2, which is equal to 24. Okay. So what if I take this 4 factorial, which is 4 times 3 times 2 times 1, and divide it by 6 different combinations of orderings for 3 letters. Take a look at this. I'm taking the permutation of 3 objects out of 4 objects, and I'm dividing that by these 6 different combinations of orderings for 3 letters. What do I get? I have 4 times 3 times 2 divided by 6. I can cancel out these 2. The outcome is equal to 4, which is the answer to your combination. So by dividing your permutation by the total number of orderings that you have, you can actually get your combination. So here's a nice formula for you. The combination are objects out of n objects is usually denoted by C of R out of n, which is n factorial, divided by n minus r factorial. So far it's very similar to your permutation. On the denominator, you also have to write r factorial. R, 3 factorial, 3 times 2 times 1, which is 6. So we get the outcome that we're looking for. Let's go over some examples. We are on page 5. So the question says, what's the combination of the following? Example. Compute the combinations. Very well, the first one says, what's the combination of 3 objects in total, and you're selecting 1 object out of those 3 objects. So in another word, you can say that, hey, how many subsets with only 1 member I can form from a set with 3 members? So first of all, the combination of R objects out of n objects, it has a nice formula. N factorial divided by n minus r factorial, and on the denominator you have to include r factorial to get rid of all of those orderings. Very well. So what is n? N is 3. What is r? R is 1. So let's follow the formula. 3 factorial divided by parentheses 3 minus 1 factorial times r factorial. What is r? R is just 1 factorial. Well, this is equal to 3 factorial divided by 3 minus 1, 2 factorial. And note that 1 factorial is just equal to 1. So we're not actually worried about 1. You can copy 1 down, or it doesn't matter. On the numerator, you have 3 times 2 factorial. On the denominator, you have 2 factorial. Now you can cancel out 2 factorial, and you get to 3. I'm going to give you one example that actually illustrates what's going on in this calculation. So this question asks how many subsets with one member. This R shows the number of elements in the subset. With one member is possible from a set with 3 members. Okay, consider a general set. Suppose set S is equal to the set including 3 objects, like A, B, and C. How many subsets you can form that have only one member? Okay, that subset can be a subset including A. It can be a subset just including B. The cardinality of each of these sets is equal to 1. And the set including C. How many? 1, 2, 3. 3 subsets. Okay, the second one. The second one says, hey, what's the combination of 3 objects out of 6 objects? N is 6, R is 3. So you have 6 factorial divided by parentheses 6 minus 3. 6 minus 3 factorial times, on the denominator, we have 3 factorial, which is equal to, well, let us do the computation here. I see a 3 factorial, so I'm going to expand 6 factorial as 6 times 5 times 4 times 3 factorial. Because I have a common factor down here, I want to get rid of this. And 6 minus 3 factorial is also 3 factorial. I'm copying down my 3 factorial here, and I'm canceling 3 factorial, 3 factorial. What's left? 6 times 5 times 4 is left. So I have 6 times 5 times 4. And on the denominator, 3 factorial is 3 times 2 times 1, which is 6. 3 factorial is equal to 6. Why I write it this way? Because I want to cancel out 6 and 6. What's left? 5 times 4, which is 20. Excellent. It means that if you have a set with 6 elements, how many subsets with 3 elements are available? Those are 20 subsets with cardinality 3, which are available. Another example for you. Well, in this example, it says you have 5 faculty members. So let us have 5 faculty members. How many 2-member committee can be formed? So here we have 5 faculty members. 5 faculty number 1, faculty number 1, faculty number 2, faculty number 3, faculty number 4, faculty number 5. How many ways we can actually form committees with only 2 members in them? So it can be a set including faculty number 1 and faculty number 2. You can form a set with faculty number 1, faculty number 3. You can form a set with faculty number 1, faculty number 4, and you can form a set with faculty number 1, faculty number 5, and you can continue this process. How many subsets do you have? Well, we know that ordering is not important. It doesn't matter if you select the first faculty, then the second faculty, or the second faculty, then the first faculty. Ordering is not important. This is an example of combination. This is combination or selection of two objects. In this case, you have faculty members, objects from 5 objects. So the combination of 2 out of 5, which is, if you follow the formula, we get 5 factorial, n factorial, divided by n minus r factorial, 5 minus 2 factorial, times r factorial, which is 2. There we go. So let's simplify it as much as we can. First of all, I have 5 factorial. I can write it as 5, 4, 3, 2 factorial, divided by 5 minus 2, 3 factorial, 2 factorial. You could say, hey, Professor, it wasn't easier for you to write this as 3 factorial? I say, yes, of course. Well, let's do that. 3 factorial, you can get rid of them. 2 factorial is equal to 2. 4 divided by 2 is 2. 5 times 2 is 10. 10 different possible committees are available. You can actually list all of those subsets and actually see there are 10 of them. So here you can write faculty number 2, faculty number 1, we already have it, we're not going to list that. Faculty number 3, then you have faculty number 2, faculty number 4, then you have faculty number 2, faculty number 5, then you're going to start by having faculty number 3, faculty number 4, faculty number 3, faculty number 5. What else? Faculty number 4 and faculty number 5. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 of them. Exactly 10 subsets with 2 members, or cardinality of each of these subsets is equal to 2. 2-member committee. Well, now an interesting question. Suppose I give you a word like book, and I ask you how many permutations or ordering is possible? Question. How many permutations of word book is possible? Okay, book. How many letters do we have? So you might say, hey, I have B, I have O, I have another O, and I have K. Let us start. So we can write D as the first letter. Then you can write O, the second O. Okay, then K. Or you can say that, hey, I want to write down, for example, K first, then O, and B. Okay, there you go. What else? I have O, B, O, K. I have K, O, BO. Then I have, let's see, BKOO, OOBK. Then I have OOKB. Or what else? Do we have any O? If I write O, I can write BK, KB in the middle as well. Oh yeah, of course. OO, KB, OO, BK. Okay, what else do we have? So we started with OO, BK, KB. Then we started with B, O, OK. Then we have BKOO, KBOO. Do we have KBOO? No, we don't have KBOO. Then what else do we have? Just trying to again all of them that are possible for us. Then let's see. Starting with K, OBO. Okay, we have that one here. I need more combination, more ordering. So more combination with ordering, you can say that, which is equal to permutations. Let me see. Will be okay. Okay, OB, do I have that? Okay, OB, so let me write it here. So I have okay, OB as well. What else? What else is missing? Let's see. What if they write let's see, something else. I'm trying to think of the last one. I know we missed something. BO, let me see. I'm looking for one BO. BO. BO and KO. Okay, very well. I think this is the last one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and just 12. It's not like saying that, hey, I have two different O's and I want to switch these two. So you cannot say that this is my first O, this is my second O, these are different from each other, so I'm going to have BO, OK. This is wrong. It's not a different ordering because you have the exact same letter repeated twice. So you might say that if I want to follow the formula for permutations of n objects, which was n factorial, remember that this formula works if you have distinct objects, distinct letters in your collection. Now that you have repetition, we're going to use a different formula. What are we going to do? We're going to actually get rid of all of the orderings for the same letter or object that is repeated in that question. So here you have 1, 2, 3, 4. I know these are not distinct objects, but on the numerator, what if I write 4 factorial? B, O, and K. Now I'm going to divide write this by permutations of these two O's, which is 2 factorial. Take a look at this. Here you get 4 times 3 times 2 factorial divided by 2 factorial, which is 12. 12 permutations. Here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 permutations. Well, we have a general formula. So let us write it down here for you. So the permutation of n objects with some of them repeated like this. Suppose you have n1, n2, n3, n4, and the rest repetitions of some of the objects out of those n objects is going to be n factorial divided by n1 factorial, n1 factorial times n2 factorial times n3 factorial, and so on. So this is the general formula. In this case, in this example, we don't have any repetition for B, we don't have any repetition for K, but we have repetition for O. O is repeated twice. So 2 factorial goes on the denominator. We can write it as 4 factorial, which is n factorial divided by 2 factorial, and we saw that it is equals to 12.